No, don't touch that one. This one, I think, yeah.
Yeah. Awesome. All right. Thanks to the conveners for having me. It's been great. It's fun to see everybody in person. I'm Noah Phillips. I'm at Lakehead University, Hawaiʻi University in Ontario, Canada. And today I'm going to talk to you about plate boundary fault law, and in particular, subduction zone plate boundary fault law, and some observations, conundrums, and potential future directions. This is a field photo from the Mugi Melange, which is the case study I'm going to show you today. And it's a really amazing exposure of an exhumed subduction plate boundary, where you get nearly continuous exposure along the coast. And so you can walk from what used to be the downgoing oceanic plate through the sediments that were sitting on top of it, and then into the overlying accretionary prism. Yeah, so this was done with a bunch of other people, obviously, and I might say some controversial things at the end. And so if you disagree with anything I say, that's all my fault. And if you really think that stuff's cool, obviously, that's all on them. All right. No. Yeah, that was fun. Good. All right, so the talk's going to be in 3 parts. I'm going to give a very brief overview of styles of subduction zones, and this will be very brief because Damien and Donna have really nicely set me up. Then I'll go on to this case study of the Mugi Melange, and we'll talk about what we've learned from these fault rocks, and then some thoughts on moving forward as a community. So styles of slip and subduction zones. I mean, I think everybody knows subduction zones are important. There's a lot of hazard assessment, which relies on understanding the modes of slip and subduction zone and the rheology of subduction zone. And this has been talked about a bunch already, but there's kind of this old conceptual model where a lot of subduction interfaces are locked between 100 and 350 degrees centigrade. And then above that and below that, there's kind of free slip, which loads that locked interface and eventually causes big earthquakes. Since these conceptual models have come out, so there's been a lot of really interesting observations about other modes of slip happening within subduction systems. These include slow slip, which is slow movement, transient along the deep subduction interface. And then during these slow slip events, there's also tremors, some sort of chatter going along on the interface. It's believed to be, somehow intimately related to movement of fluids. Within that chatter, you can pick out individual events. These are called low frequency earthquakes. And these earthquakes have focal mechanisms which show the same kinematics of slip as slip along deep subduction interface itself. And we see these episodic tremor and slip along most subduction margins where there's enough instrumentation to see it. And likely, we'll see it almost all subduction margins with more instrumentation. Slow slip also occurs in the shallow subduction environment, as well as in strike slip fault zones. And it generally occurs if the subduction zone is not locked all the way to the trench. And it seems to be intimately associated with kind of subducting topography, that Damien mentioned earlier. And then they also seem to be associated with low velocity zones due to high pore fluid pressures in both the deep and shallow environment. Okay, so now we'll get into looking at some rocks. So what I want to show you today is this exhumed melange. It's a late Cretaceous melange, so it was active about 60 million years ago. It represents an exhumed subduction zone where the subduction interface was underplated to the accretionary prism above. And what's nice is that there's a series of kind of late faults that cut through it. So when you're in the field, you walk from this underplated oceanic basalt, that's all these green lines, through the sediments that were sitting on top, then back into another sliver of this underplated oceanic basalt, then through these sediments sitting on top, and eventually you make your way into the overlying accretionary prism. It looks complex, and it is complex, but that's what subduction zones are, and it's kind of exciting. So in the middle of this melange, there's this out of sequence thrust, and it kind of separates 2 temperature domains. So this lower Mugi Melange deformed temperatures of about 140 degrees, and this upper Mugi Melange in the light gray deformed the temperatures of about 109 degrees. And what's exciting is there's textures for both fault creep and large megathrust earthquakes and potential slow earthquake phenomena. So for those of you who are not into looking at rocks, I'm going to keep it relatively simple. There's kind of four main rock types. There's the basalt, which represents the underplated oceanic crust. When you get close to the contact with the sediments, usually about 2 meter thick package, you get this altered basalt, which is from the loss of olivine and pyroxene and gain of chloride and albite. Then you enter into this gray unit, that's subduction melange. It's got a shale matrix and then blocks of sandstone and basalt sitting in it, and these kind of seams of volcanic tuff. Then finally we get above it into this accretionary prism, and this is a quartz-rich sandstone. And once you get into that, it's relatively undeformed. You can see the turbidite is really clearly in it. So you go from basically relatively undeformed basalt into really deformed altered basalt, really deformed shale matrix melange, and we'll look at those in detail, and then back up into this relatively undeformed quartz-rich sandstone. So what's exciting here is that there's 3 locations which display really concrete evidence for big earthquakes, so paleoseismicity. And 2 of these occur within that altered basalt, and then 1 of them occurs within the overlying, at the contact between the melange and the overlying turbidites. So these 2 that are within the altered basalt either formed like right on the plate interface or during this underplating process. I think it's more likely that they formed right on the plate interface. And the one that's at contact in the accretionary prism, it's happening somewhere in here, at this upper interface between the subduction melange and the accretionary prism. So what do these look like in the field? How do we know that they're earthquakes? So this is one example within the altered basalt. This is what's known as a fluidized cataclysite. So it's a really finely ground up altered basalt. And you can see it injecting here into overlying shale. And that injection is caused by near lithostatic pore fluid pressures. And so this is hypothesized to have formed due to shear heating on fault during the earthquake, causing expansion of the fluids and then injection of that kind of slurry up into the overlying melange. To further support that, these calcite veins have these stretched fluid inclusions in them, which are indicative of a co-seismic temperature rise right here along this space. The other location where we found evidence for an ancient earthquake of these altered basalts is here in this little fault. It's pretty close to the shale altered basalt contact. This is a hand sample, so you can see the scale is pretty small here. And if we zoom in to a small section of this, you can see this fault here, which has 3 generations of basically broken up altered basalt. And within one of these generations broken up altered basalt, there's these kind of sub-rounded dark clasts. When we look at those sub-rounded dark clasts in detail, you get these, this is in the SEM, the scanning electron microscope, and the brightness here is basically a relationship to density. And what you can see is that there's these like labs of plagioclase that have these kind of complex zonation patterns. There's these rutile grains which have big margins, and that's because of partial melting around the rutile grains. And then you have these cross-shaped oxides, which are indicative of rapid punching from a melt. In some other areas, you can get this kind of more matrix microstructure where there's kind of a ground mass, which has a relatively consistent composition. And then these disseminated iron oxides, which are also indicative of rapid punching from melt. The third evidence of paleoseismicity is at that shale sandstone boundary. So that's this fault here. You can see me for scale. Don't use Kotaro Uchiha here for scale. You got with this stitching of images, you got turned into like a little Pokemon character. But you can see this fault here. It's about 2 meters wide. It's pretty complex, like all faults. So if you zoom into it, it's got a mix of these like bigger sandstone clasts. And then within the fault itself, you can see these really thin dark seams cutting through it. And if you look at the microstructures of those really thin dark seams, again, you see evidence of rapid punching from a melt. So these are ancient earthquakes where there's frictional sliding, the temperature rose enough to melt the rock, and there was rapid quenching form that's due to tidal wave. So some quick takeaways. We have faults displaying evidence for earthquakes, post-seismic weakening, and these tend to occur right along the boundary of this shale melange, which is several hundred meters thick, and either the oceanic plate sitting below it or the accretionary prism sitting above it. And so what's going on within that 200-meter package in that shale matrix? So these rocks look way more complicated, and they are way more complicated. So this is the shale matrix here. You can see clasts of sandstones of different size. They have all these veins cutting through them. And this really strong fabric here in the shale is caused by dissolution of soluble materials that are getting redeposited within these sandstone clasts in the vein. You can see little seams here. This light gray stuff here is volcanic tuff. It's kind of dismembered and strung out within the matrix. If we look at kind of bigger sandstone clasts in this shale melange, you can see that there's kind of these big overgrowths on the sides here. This is indicative of fault distributed shearing within these rocks. But you can see if you look on the margins here that there's not much cataclysite. There's not much grinding up of the rock or localized slip along these surfaces. However, when we found basaltic blocks within the melange, you get these really nicely developed cataclysites, and you get, evidence of slip along the margins, those slicken lines like that. So what we did was we mapped kind of some key areas in detail to look at these like localized slip surfaces along the edges of these basaltic blocks within that shale. So we took out a drone and made these kind of high resolution base maps. Then we make all of our structural measurements, look at the rocks with that. And these maps of basaltic blocks form 3 arrays. This is just showing one of the arrays here. And they're relatively continuous across the mapping area. So they go for, a couple hundred meters before they peter out into the ocean or head into the trees where we couldn't find them. So looking at these basaltic blocks, what they have in general is these kind of relatively unaltered cores. That's what I have colored in dark green here. And you can tell they're unaltered because the magnetic susceptibility on them is still quite high. And then when they get altered, the magnetic susceptibility goes way down below. This stippled region is showing the area where there's cataclysites, so that ground up rock. And then these pink lines here that are probably really hard to see are showing individual slip surfaces. And you can follow these slip surfaces from block to block, which is kind of exciting. So if we look closely at kind of one of these slip surfaces that I call a linking structure going from block to block, and again at the margin of one of these blocks, we'll start at the margin of a block. And we look at it in stupid amounts of detail. You get these altered basaltic cataclysites that have a ton of veins running through them. So all these white lines cutting across their different veins. And if we zoom into the veins, you can see different orientations to the veins. So we have these tensile veins, they're relatively high angle to the block. And then we have these shear veins, which are offsetting the tensile veins. These are mutually cross-cutting one another, indicating that this kind of cataclysite formation is happening at really high pore fluid pressures. Looking at these linking structures, so you can see this is an example. This is the field photo of a linking structure, and you can see this little bit of altered basalt getting strung out between these different blocks. And if we look at those again in like stupid amount of detail, you can see that the altered basalt is all broken up. And then there's these kind of through-going slip surfaces, really finely ground up altered basalt. So to simplify this as much as I can, this is a single interface between altered basalt here on the lower half of the image, the shale matrix on the upper half. And you can see the shale matrix has this really strong fabric that's formed from this pressure solution process. And the altered basalt has these localized faults cutting through it, right along the shale altered basalt margin. And so we hypothesized that, this localized faulting with the altered basalt could be because the altered basalt is velocity weakening, while this kind of distributed deformation in the shale could be because its velocity is shrinking. We ran some friction experiments at the lab at Rice University with Melody French, and we took altered basalt and the shale and ground it up, and we put it in this saw configuration and then sheared it, see what would happen. And we did that for a number of different rate steps to get at the rate of state parameters, and we did this at kind of in situ conditions. So temperatures of 150 degrees, pressures of 120 megapascals, and pore fluid pressures that were hydrostatic or elevated. And what you can see is that the shale matrix was consistently weaker than the altered basalt. And if you look at individual rate steps, the altered basalt showed velocity weakening behavior, so consistent with those microstructural observations we saw, and the shale showed velocity strength behavior. What's kind of exciting about this is at these conditions, the shale velocity strengthening, fresh basalt is also velocity strengthening. It's just this altered basalt here that shows this velocity weakening behavior. So we hypothesized that, these altered basaltic blocks could be kind of little sources or LFEs, and then linking these together could form, kind of a larger magnitude slow earthquake at very high fluid pressures once the blocks were kind of sitting close to this critical nucleation length scale. Yeah, I think I said it. We want to go back. All right, and then slow earthquakes probably caused by increasing slip rate in the shale, which could cause or be caused by an increase in failure rate of these blocks. So the takeaways here: that localized slip within altered basalts and a substantial shale interface is happening while I boogie, blah blah blah. The rock type exhibits velocity weakening behavior at in-situ condition. That's the altered basalt. And there's evidence for distributed creep within the shale matrix. We hypothesized that mixing velocity weakening altered basalts to this velocity strengthening shale matrix may lead to kind of these slow earthquakes. And one thing I want people to take away from this, especially people who are early career scientists themselves, is that we learn a lot more by working together. And it's okay to just randomly talk to people at workshops if you have an idea. So that those experiments I did, that was from talking to Melody French at a workshop like this. And the field work even in Japan was just by cold emailing Luigi, setting up a collaboration. So, some thoughts on moving forward. Some of these are going to be pretty geology focused, but one thing that we're really good at is recognizing those earthquakes in the rock record. There's this thermal pulse that's permanently imprinted on the rock. And we can kind of hypothesize, or we can get at really slow, steady state creep as well in the rock record, but we're really bad at these intermediate strain rates and these strain rate fluctuations. And I think this is a big area where people could work together to kind of develop new tools and models, especially geologists, geochemists, experimentalists, to try to find good evidence for intermediate strain rates in the rock record. So my potential LFEs are definitely just a hypothesis because there's no way of confirming for sure that these slip surfaces deform at an intermediate strain. Constraining rock strength in the field is also really tricky, and I think it's something that we could get a lot of people working on together. You can see I'm from Canada because there's almost like a socialist theme at the bottom here. What we need to develop these kind of new piezometers to better constrain rock strength in the field so that we can independently assess flow laws developed in the lab. And without that, we're just kind of going along with whatever the people in the lab say. We say, oh, our microstructures kind of look like this, therefore this strength. It would be great if we could look at rocks in the field and say, this rock deformed at this stress, and then compare that to flow laws developed in the lab. But it needs a lot of work from a wide group of people all working on it together. Same thing in the lab. We need more experiments on a wide variety of rock types. This is my own personal bias, but there's a lot of work done on quartz, and we could we probably know enough about quartz at this point. And it would be nice if there's a larger number of higher risk experiments that are more long duration and kind of as close to realistic conditions as we can get in the lab, which I know is hard and it's high risk and they take a long time, but they have very large rewards if they work. And then finally, geologists are way slower at digital data infrastructure than the geophysicists. So the geophysicists have UNAVCO, you've got IRIS, they're wonderful repositories. And this is an example of what I did during the pandemic when I couldn't go to the field, was I just like, look up a ton of studies on different things, make big plots and try to compile them. And it's a huge amount of work because we don't have this digital data infrastructure. And I think as a community, it's time that we really invest in the things that are currently being developed to make our geologic data more fair. So currently, most of the geologists are just kind of dumping things to the OSF or in their own institutional repository and a statewide repository. But this doesn't make it findable. It's all scattered all over the place. You still have to go to the paper, read it, find their repository, go to it, download that data. But there are things going on right now. So this Travis Spot initiative's made this really beautiful field app for people who have used it in its early days. It really sucked, and now it's much better. And it's amazing. I can't tell you how much faster it is mapping in the field with this app than when I used pen and paper. And with a click of a button, it all gets stored in a permanent repository. They've also developed one for microstructures, and this is really exciting. So you can do all your thin section observations, click of a button, upload it all to a repository that's searchable. And the searchable functionality is really nice. You could search by all sorts of different features, pops up where they made those observations around the world. And yeah, I think it's really going to change things for us and will lead to bigger discoveries, more big data. And finally, I'm really excited about the SC4D stuff. I love this idea of community field sites to work on problems together. And I think the observations of the movie of these different earthquakes and potential slip surfaces, it's taken 20 years, hundreds of papers to get to where we are today. I think we could make a lot of really ground-based discoveries by working together on a couple sites and getting a lot of boots on the ground, discuss things together in the field. And that's it. Thank you.
I'll take a few minutes for questions for any of the speakers. Yes.
Well, I'll start with one because I lost track. Could you remind us what depth those rocks were at?
Yeah.
Seeing the both styles of slip.
So the temperatures are 140 and 190 within those two domains. And you see both styles of slip in both domains. So at the 140 and at the 109. So like that fluidized ultracataclysite that it's injecting into the shale above it, that's in the 140 centigrade section. And then that little bit of frictional melt within the other cataclysite was in the 190 degree section. The depths are more poorly constrained. Temperature comes from Raman thermometry on carbonaceous material. The depths are trickier. It's that area of the Shimanto accretionary complex has pretty high geothermal gradient because it's hypothesized that there was a ridge going down around that time, which helped everything to get underplated as well. So the depths could be anywhere from like 4 to 9 kilometers, depending on what assumptions you make.
Right, so probably towards the up dip end of the site.
Definitely at the up dip. Exactly.
I also have a question, you're talking really nicely about sort of shallow slopes, but how similar do you think things that are happening down dip of the seismogenic zone are to up dip? Is it similar mechanisms in different materials? Is it different mechanisms in the same materials?
Yeah. So I had a slide on that and I took it out. I was running long when I practiced this morning. So at the down dip limit, there's obviously some major differences. One is like you're way hotter. So the matrix is probably, well, depending on how you believe, it could be deforming through pressure solutions free still, or it could be dislocation free within that material that's hosting all the blocks. And there's kind of two main hypotheses right now from the geologic community about what flow earthquakes look like at those depths. One is very similar to this, where it's like blocks of harder material that are failing in a brittle manner that are causing these, tremors and LFEs and VLFEs. There's another community that's looking at quartz veins, and there's kind of silicon fibers within them, and they hypothesize that those could be LFEs and VLFEs. The quartz vein stuff may work at depth, but it really doesn't work in the shallow environment because the kinetics of like silica precipitation are completely different. You're in a completely different thermal regime. So this stuff is similar to the block hypothesis for the stuff that yeah.
Good.
Actually, maybe a question for all three of the speakers, but it seems like one thing that we all wrestle with is trying to make sense of what we're seeing in geophysical images, what that means about what the conditions are, what the materials are. And I was struck in Zach's talk that it seemed like maybe we have a better handle on that in certain kinds of materials, or maybe we don't, I don't know. But certainly in subduction zones, it's kind of messier. I guess I'm kind of curious about your thoughts on that. Is there hope? What should we be doing? Is arithmetic simpler because the materials are more organized, or is it actually there's still a ton of uncertainty that for other reasons, like H2O content, whatever else. So yeah, I don't know, kind of open question, I guess.
Yeah, I mean, I think we really need within this community, within the people more broadly, we need to have those kind of linkages built into the way that we construct our models. So one thing that I is that we need to sort of, in particular, move our uncertainty space away from like the strict geophysical observations, like what's the uncertainty and velocity, and have those kind of through going forward calculations that allow us to put the uncertainty space into the thermodynamic parameters and maybe composition, and sort of have use those to try to fit all the way through clever forward models to fit the data. Because otherwise we sort of, here's some velocity, and as I showed today, you're like, okay, well, there's perfect trade-offs. So, but from a Bayesian perspective, if we go one step further back to the actual conditions of the Earth, I think that's going to be helpful. But of course, to do that, we need to have faith in that forward model connection from all the way from the thermodynamic parameters to the seismic observables.
Yeah, I would just to add on to that, I feel like a real challenge for our geophysical imaging of something like or of subduction zones and rifts is that we see, like at least in the crustal scale, the cumulative structures that are formed over the whole life. And what I thought was so beautiful in Noah's talk and other exposed megathrust you see is that you have this wide zone of cumulative deformation, but maybe you have the actual like earthquakes are localized on a tiny part of that, and it really calls for an integration of the two to untangle like the cumulative structure formed over some time from where deformation might be happening at any one moment, and for maybe higher resolution constraints on where deformation is occurring within those zones too. All that together. Only a partial answer, but I'm sure when you thought about it.
Okay, we have time for one last question. Go ahead.
I actually wanted to add to what Zach was saying and maybe provide one example. So Zach did something that I think is really clever. Maybe he underplayed a little of putting up P melts with those velocities, right? So that's that kind of thermodynamics coupled to geophysics. One uncertainty the seismics has is it can't really tell you about anything with the volatile content in those melts, but EM can. And so it's just like a perfect example of why this community is so great, that when you start talking to each other, you realize that coupling these data sets have very independent constraints and non-uniquenesses, but together really, really, really narrow that down. And then we can argue about the details of each one, but they'll continue to improve over time. So sure, our interpretations will evolve, but we're doing very little of that at this point. And I feel like we're ripe for that. We have all those things there. We just need to talk to each other and do it.
Okay, I'm sorry, we're gonna close the question and answer session right now and turn it over to Helen.
Again, let's thank